Welcome to Endless Learning Training Series, the membrane-based desalination technology.
In this video we will study about best CIP time for SWRO plant, how to find best CIP time, traditional approaches versus ML-based approach for CIP timing. The cleaning in place (CIP) process is a critical aspect of maintaining the performance and longevity of a seawater reverse osmosis (SWRO) system. The timing of CIP is an important factor that affects the efficiency and effectiveness of the cleaning process. Several factors influence the optimal timing of SWRO. Most membrane manufacturers recommend cleaning when normalized permeate flow drops 10%, normalized salt passage increases 5 to 10%, normalized pressure drop increases 10 to 15%. Normalized data are critical in determining whether one of the key cleaning criteria is met. It is recommended to clean an RO system when any one of the key cleaning criteria is met as per manufacturers. If cleaning is not done in time, then standard cleanings may be ineffective. This could lead to the need for extreme cleanings, which can cause damage to the membranes permanently. Fixed time intervals. In this approach, CIP is performed at fixed time intervals regardless of the actual system conditions. For example, CIP may be scheduled every week or every month. However, this approach does not take into account the real-time variations in system fouling or scaling, leading to potential inefficiencies and unnecessary cleaning cycles. Visual inspection. Visual inspection involves manually monitoring the condition of SWRO membranes or other system components. Based on the observation of fouling or scaling, CIP is scheduled. While this approach provides some flexibility, it heavily relies on the expertise and experience of the operator, which can vary and may lead to inconsistencies in scheduling. Rule-based methods. Rule-based methods use predetermined criteria or thresholds to trigger CIP. For example, if the permeate flow decreases by a certain percentage or if the pressure drop across the membrane exceeds a predefined value, CIP is initiated. However, these fixed rules may not capture the complex relationships between various parameters affecting fouling or scaling, resulting in suboptimal timing decisions. Data-driven decision-making. The ML-based approach leverages machine learning algorithms to make data-driven decisions on CIP timing. It takes advantage of historical data and real-time monitoring to identify patterns and correlations between various system parameters and fouling/scaling behavior. This allows the ML model to learn and predict the optimal timing for CIP based on the current system conditions, limitations, requires data availability and proper model training. Adaptability and optimization. Unlike fixed time intervals or rule-based methods, ML models can adapt to changing system conditions and adjust CIP timing accordingly. They can capture complex relationships and nonlinearities in the data, enabling more accurate predictions. ML models can continuously learn and improve as new data becomes available, leading to optimized CIP timing decisions. Limitations: requires data availability and proper model training. Cost savings and efficiency: by optimizing CIP timing, the ML-based approach can help minimize unnecessary cleaning cycles and reduce downtime. This leads to cost savings in terms of energy consumption, chemical usage, and maintenance efforts. Additionally, ML models can help prioritize CIP tasks based on the severity of fouling or scaling, further improving efficiency. Limitations: requires data availability and proper requires initial model development and implementation efforts training. Compare traditional approaches for determining CIP timing with the ML-based approach. Limitations of traditional approaches and the potential benefits of ML in optimizing CIP timing. In traditional approaches for CIP timing, limited flexibility. Traditional approaches often lack flexibility as they rely on fixed time intervals or predetermined rules. They do not consider the dynamic nature of system conditions and may lead to suboptimal CIP timing decisions. Subjectivity, visual inspection and operator experience play a significant role in traditional approaches. The subjectivity of observations and decisions can introduce inconsistencies and biases into the CIP scheduling. Manual effort: traditional approaches require manual monitoring, observation, and decision-making. This can be time-consuming and may require dedicated resources for ongoing system evaluation and CIP scheduling. In ML-based approach for CIP timing, data-driven decision-making, the ML-based approach utilizes historical and real-time data to make CIP timing decisions. It leverages patterns, correlations, and complex relationships in the data to optimize CIP scheduling. Enhanced accuracy: ML models can capture intricate relationships between various system parameters and fouling/scaling behavior. They can adapt and learn from data, leading to more accurate predictions of the optimal CIP timing. Automation: ML-based approaches can automate the CIP timing optimization process. Once the ML model is trained, it can continuously monitor system conditions and make real-time predictions for CIP scheduling without the need for manual intervention. Continuous improvement: ML models can be regularly updated with new data, enabling continuous improvement in CIP timing optimization. They can adapt to changes in system conditions, ensuring that the CIP timing remains optimized over time. In summary, traditional approaches for determining CIP timing in SWRO systems rely on fixed intervals, visual inspection, or rule-based methods. These approaches may lack adaptability and precision. On the other hand, the ML-based approach utilizes historical and real-time data, enabling data-driven decision-making, adaptability, optimization, and cost savings.
Thank you for watching this video.